Okay, so in the previous lecture, so previous lecture, we talked about the fundamental group of a space. The fundamental group of a space X. And we also talked about paths and loops, as well as, I suppose, homotopies between them, and differentiating various spaces via their fundamental groups. So that's what we did in the last lecture. So the fundamental group, which we denote via the symbol pi, x at some base point. So if our space is a subset of the universal space of all femboys, then x sub 0 is our base femboy. And the class of all paths in X, or all closed paths in X, or the path homotopy equivalence classes of X, with concatenation, which takes two inputs and takes them to some new value. Oops. Takes them to some new value, which is, I suppose, X concatenated with heap X. So with this operation, this set forms a groupoid, which is the fundamental groupoid of X. And we've shown that, or we've explored that when two spaces have separate when two spaces have separate fundamental groups, they are not the same. So this is what differentiates a torus and a circle. Now, not only because of the fact that a torus has a hole in it, but also because its fundamental group is different than a sphere. Okay. We also talk more about the fundamental group, and also defined this as a map from a K cell, a unit K cell, onto our space. And we've also stated that a convex subset has the trivial fundamental group. So a convex subset, such as a circle, you notice that if we connect two points along its boundary, or along it, not really its boundary, but along it, they stay within the set. So this is a convex, and this is also a subset of R. If the values that x, y in this circle take on are real value. So in this case, well, this has a fundamental group of 0. And also, I don't think we've done this yet, but we want to show that a pair of thighs, pair of femboy thighs, are actually sort of like this, sort of like a circle, and thus they have a fundamental group of 0. So that's what we're going to be going into today. Okay, so let's just erase this so that we can go back to lecture. Okay. Cool. So, theorem. Theorem. So the theorem states that a pair of a thigh is homeomorphic to S1 and thus has the fundamental group pi of THIGH at some skin cell x0 is 0. Okay, so what we're saying is that a thigh can be deformed into a circle. So you can take out this value. So one justification for that is, yeah, let's just show the proof. So proof. So the proof of this is very trivial. You just need to show that a thigh can be deformed into S1. And because it can be deformed to S1, we can think of it as S1. And then correspond a fundamental group to that, so we first take every point in thigh to S1, and then we're gonna, of course, get the fundamental group of S1, which is 0. So if you remember, you guys remember, S1 is the set of all points. It's basically a shell, but one-dimensional. It's just a ring of points or a circle of points. The inside or the area inside that doesn't matter because that's B1. Okay? The region enclosed by a circle, so the area inside the circle is not in fact the circle, but rather its boundary. So every point along the circle, not the inside, is exactly S1. So, or the collection of all points that lie on this circle and not inside it or outside it are S1. B1 is the closure of S1, or the interior of S1. So B1 is roughly equivalent to the interior of S1, or the closure. But I think it's really the interior, not the closure. But that's not our focus for today. Okay. So we defined, of course, when we're thinking of two thighs, they're not homeomorphic to S1 because, well, they're separated and they are two separate objects which have a disjoint union. Well, the original femboy thighs are two separate objects put into one set, whose representation is basically just thighs. So it's a hyperbolic function, and then we restrict it, and then we make some new line, or a new vertical or horizontal line. We construct a horizontal line, and then we restrict its domain to between 2 points that we restricted on the thigh. So, right, if we make this here our xy axis, both real valued. Okay, so let's say we want to draw one thigh. So first, let's construct a line, which I will call C, and then construct a hyperbolic function, which is the thigh itself. You guys can make it thin or fat or whatever. It's just, we restrict it to values here. The values wherein it crosses, or x values were in this function crosses C. So we erase the parts that go off to infinity. And then, lastly, once we know where it intersects, we restrict C as well to only be the values between those 2 points. And so we have a thigh. This is a thigh. And you notice that, well, yeah, it is homeomorphic to a circle. We just need to squish it, round out the edges over here, and then we got something that's akin to that. And it's also a convex set Because notice that if I take 2 points here, 2 points, 1 point here, 1 point here, and I connect them with a path of points, they stay within that subset. I know it wouldn't make sense if I did this in F space, but okay. Let's say we direct a bunch of femboys to form a parabolic line, such as this, and then we did exactly what we just did a while ago, but instead of just constructing it, we direct a bunch of femboys to do that stuff, okay? So we take out some femboys, we restrict some femboys, and we take out some femboys, we find femboys where they intersect, and then, restrict it to those femboys only. Tell those to go home, and then we pick 2 femboys, and then we take back some of the femboys we sent home, and then line them up between those femboys, right? And if those femboys stay within the gigantic line of femboys, or outline of femboys, it is convex in F. Okay? Okay, so now, since it is convex, and this is simply just a subset of R, then it must have the fundamental group 0. So even if this set here is, even though it's some wacky shape that is somewhat, it's a bit weird, but in the end we can form it to S1. It can have this fundamental group. Now the homeomorphism. Well, the homeomorphism isn't exactly or can't be put into really algebraic terms. That would require some stuff here. But we'll just know that any point here on the thigh, so any point on the thigh is sent, because this point here is composed of 2 coordinates, x, y, are sent to an x, y, or sent to a pair, or sent to their corresponding pair, x, y, in S1. Okay, so that's our homeomorphism, at least, or a rough picture of it. Okay, so I'll say here, there exists. So this certain map. So once we morph these points onto some other point, right? Once we morph it, we just take its fundamental group, which should be 0. I mean, of course, the S1 can't be any other shape other than itself, right? I mean, it can certainly be a triangle, it can be a cube, you can deform it into those shapes, but ultimately, those guys, since they are convex subsets of R, they have fundamental groups of 0. So, what if I have an alien femboy that has thighs that are triangular, like extremely triangular, like it's perfectly triangular like this. Well, since it is a convex subset, or since its model or picture in R2 is the convex subset of R2, then it has a fundamental group of 0. So this theorem is not only applicable to a thigh that is parabolic in shape, the conventional human thigh, but if we try to abstract the word thigh to any shape that is homeomorphic to S1, that resembles a human thigh, then it is bound to have a fundamental group of 0. So I guess we don't really need to write down the group, we just explain it. Just say that there is a homeomorphism, because you'll notice that there is no holes in it, right? You just construct a loop inside, and then infinitely tighten that loop. And if the loop doesn't stop, or cannot be shrunk any further, then that is definitely homeomorphic to the circle. Okay. Or if you want to say B1, I guess B1 is a different case, but yeah. I digress. Okay, so I didn't discuss this, but let's make another definition. Def. A space, let's call it F, in big F, so this is a space of femboys, is, so I just need to note here that F here, this 2-dimensional space or 3-dimensional space or n-dimensional space, is right now, in the context of algebraic femboy theory, not position theory, right now we're treating F as a field of femboy. So literally think of a grass field and then we put a bunch of femboys in there. Think of it like that. So it's a positional type thing. So each point is a femboy. So each coordinate or each position is a femboy. It's not really a characteristics of sorts. Okay. I'm sorry if I didn't clarify that during the beginning of this course. So, all right, a space, small f in big F. Actually, I'll call it normal F in, which is subset of math cal F is simply connected if it is path connected. If it is path connected and its fundamental group independent of its base point or base femboy is 0. So I don't know if we did this last lecture, but this is the notation for a fundamental group of a femboy space wherein it's independent of the base point or the base femboy. So all homotopies or all loops constructed here, all the bases of the loops constructed here don't matter. So we can make a loop at any point here or any point here, and we could infinitely pinch it, tight, and yeah. Okay, so right. So path connected. So that means a space is path connected. Let's recall a space is path connected when every point inside the space, for every point or every pair of points or for every point inside it, we can always construct a path. So this space here, which I will call X, is path connected because if I take a point here, another point here, I'll be able to make a path that is unobstructed. But once I split X and make it into this new set, I'll call Y, it is not path connected. Of course, we can think of the subsets of Y, like this subset and this subset, and make them their own separate space. And if we make these their own separate space, of course, they are path connected on their own because you can see that they are connected and that we can take 2 points and then draw a line between them. But if we take this to be one space that has merely been separated into subsets and claim that it is path connected, we are wrong. Because notice that once we do try to take 2 points and then link them with a path, the path has to travel through space outside both subsets of the entire set, or outside the entire set. So Y here is not path connected because the path must stay inside the space. Or in general, it must have no holes in it. That's the most intuitive way of describing this space here, the simply connected space. And, this makes sense. It's simply connected and path connected. It makes sense. This picture makes sense because, and it really makes sense because notice that the fundamental group is 0. So it has the fundamental group of S1. Thus, this space, this femboy space, is homeomorphic to S1, whose fundamental group is, you guessed it, 0. So everything checks out here. That's really the beauty of mathematics. Everything checks out. And they neatly support each other. So once we got this definition down, let's make a new lemma. Now I'm not gonna prove these lemmas. I'm gonna leave it up to you guys. And these lectures are inspired by Pierre Albin's lectures. So you guys can visit the channel that uploads lectures on YouTube. So you can see the actual proof of these things. What we're going for is really intuition and the concepts behind these things. Okay. Okay, so lemma. Lemma. If F is simply connected, which I will just abbreviate as SC, then two paths FG that maps the interval minus 1, 0 to 1, to the space F, are path homotopic. If and only if f of 0 is equal to g of 0 and f of 1 is equal to g of 1. So what we mean by this picture is that these two share the same endpoints, the same starting points and the same endpoints. So of course we can picture this as 2 points here, which are f0 and fg, and then this is f, this is g. This is f of 1 equals g of 1, and this is f of 0, which is equal to g of 0. And this curve here is f, and then this curve here is g. These two are path homotopic because they share the same thing. Now, if g here has a separate point, right? If they have a separate point, if g is a separate point, say it's over here, over here, over here, then that means they are not path homotopic because we cannot deform one into the other. You notice that if it's over here, or if it's over here, when we try to deform it to the other, it really can't do that because they don't share the same endpoint. We can only form one into the other if they have the same endpoint over here. We can flatten them both or retract them both onto a single line, and then we got ourselves two similar objects, and that's the intuition behind homotopy. Okay. All right. So I'm not going to prove these things, but let's talk about the Borsuk Ulam theorem. So Borsuk and Ulam. Okay. The Borsuk Ulam theorem. This is a very important theorem in mathematics, in our study. So the Borsuk Ulam states that given a unit Femboy shell Fs2 and a map between it, so given Fs2 and a map that takes Fs2 and then send every point inside it or every point on it. It's essentially just the surface or the boundary of the unit ball, S2, onto F2. Any map, I'll call this map phi. Phi identifies at least one pair of antipodal femboys. So that's Borsuk Ulam in the context of our theory. So if I have the unit Femboy sphere Fs2 or the shell of it at least, not really the inside volume, there are at least 2 points along it such that when we run a line through them both, it crosses the center. That's antipodal. And there is at least one of them such that when we take Fs2 and then squash it onto two-dimensional femboy space, 2 femboys get mapped onto the same point. So, to give a picture here, so this is Fs2. And then we have 2 antipodal points, or antipodal femboys. When we perform phi on this, on Fs2, and take it to F2, yes, just don't mind the noise. Okay, when we squash this however way we want to onto two-dimensional space, whether it be in the form of a heart or a flat disk, infinitely thin disk, or whatever shape you want, as long as it's not discontinuous or cutting a hole in it. So basically, when we perform a homeomorphism from Fs2 up to F2, there will be, or these 2 points, or there will be at least one pair of these points, or at least there's going to be one of these points that get mapped onto each other. So let's say it's a flat disk now. Or, sorry. I will call these 2 femboys F1, F2. So let's say we squash it, or make it into some irregular space. This is the most sensible one. F. They will be mapped onto the same image. So this here is phi of F1 identified with phi of F2. Actually not identified, but equal to phi F2. So Fs2 originally exists in 3-dimensional space. It is a sphere. S1 is 2-dimensional. When we squash it onto 2-dimensional space, there will be 2 antipodal femboys that get mapped onto the same one. So they become one, or they become a new femboy in a new position over here. Okay? So that is the Borsuk Ulam theorem. Now, a corollary of this. Okay, so now a corollary of this theorem is that if we have 3 convex subsets or closed subsets of S2, at least one of these 3 sets contains an antipodal pair of femboys, or at least one pair of antipodal femboys. So corollary, that's what that is, corollary. Corollary. Let Q1, Q2, and Q3 be subsets of Fs2. Be closed subsets, or let's use the lingo in femboy theory, closed abelian blocks. Closed abelian blocks such that Q1 union Q2 union Q3 is equal to Fs2. So we divide Fs2 into 3 closed subsets. At least one of them, contains a pair of antipodal femboys. Okay. So the intuition between this is that, well, because we're mapping FS2, right? When we map FS2 onto a flat space, there will be 2 points, 2 antipodal points that get mapped onto each other. Now, if we divide FS2 into 3 closed subsets, there should be at least a point among one of them that, or there should be at least a pair of points in one of these 3 closed subsets that get mapped onto each other. And we just work the homeomorphism in reverse to identify those 2 antipodal pairs. Now, FS2 always has an antipodal pair. According to Borsuk Ulam, FS2 always has an antipodal pair that gets mapped onto the one same thing. So if we already have the morphed FS2 in F2 space, when we work the homeomorphism in reverse, homeomorphisms are bijections, or they're at least injective. Yeah, they're at least injective or bijective. Well, most of them are bijective, which means we can work them in reverse. So when we work the homeomorphism in reverse, that single point will correspond to the 2 points that it used to be, okay, before the homeomorphism. Now, it's likely that when we divide it into these 3 subsets, we will see these antipodal pairs be in one of them, or 2 of them. So, yeah, when we have a morphed version of FS2 in F2 space, and we know where that thing is we know where that point is gonna map onto, right? We work the homeomorphism in reverse. We should get 2 points now on FS2, and judging by how well we partition FS2 into these 3 closed subsets, they should contain at least 1 pair of antipodal femboys. So the intuition behind this is just we work the homeomorphism that we established a while ago in Borsuk Ulam and do it in reverse. So we work that homeomorphism in reverse. So now suppose I have a simple subset of femboys just along a line, right? Along a line. I'll call it FS1. I mean not FS1, but rather just F1. So F that is a subset of F. F1. So mathcal F1. Not F2 or F3 or what? Just one here. And then I have another one, F2. It's called X and Y, so it's more intuitive. X and then Y, which is also a subset of this. And we don't strictly say that X and Y here are similar or homotopic or what. We just say that they are subsets of F. It doesn't have to be that they have an intersection or they don't have an intersection. What matters is that in this proposition, if 2 spaces X and Y are path connected, so X and Y path connected, then there is an isomorphism between, so if we take the product between them and find the fundamental group of that product of X cross Y, and then we pick some base femboy, X0, Y0, and then group it with another base femboy in F. This fundamental group is isomorphic to a product between the fundamental groups of X and the fundamental group of Y. X at the base femboy X cross pi sub 1 of y and with base femboy y0. So prop. That makes sense because if we separate this into these two right here, it would sort of be homeomorphic, isomorphic to these two. And I suppose that isomorphism is just simply splitting it, right? Simply splitting this fundamental group into these two fundamental groups. So that's a nice one. Because these are path connected, we can simply we can construct loops, right? We can construct loops inside them. And when we take the cross between them, or actually we can't construct loops just yet because it is, it's just a bunch of lines put together. And when we do take the Cartesian product between these two, we get ourselves a two-dimensional space, F2. So at first it's an F1, but yeah, notice that this entire fundamental group exists in F2. Now you notice that when we make a loop inside here, because these two are path connected, all loops can be tightened, or at least we can construct as much loop as we want inside this space. Now, suppose I want to take that space and then make it into 2 points again. Okay? Now, there should be some correspondence between the fundamental group, or all points or all loops in this fundamental group, with points along these two separate lines. So when we take the Cartesian product of those two separate lines, we would get essentially the same fundamental group and the same loops inside them. And there's a chance that they can be squished-morph or be different, but they would still be homomorphic or homotopic to loops here, from here. Okay. 37 minutes. Okay. So now let's talk about homomorphisms. So these are functions between groups. More specifically, induced homomorphisms. Now this is going to be a bit more abstract. We sadly would not have any picture here until much later. But yeah, okay, here you go. Now suppose I have a map phi that takes the space X with its base point or base femboy X0 and takes it to Y with base femboy Y0. Now this implies that X is mapped onto Y and that the image of X naught, or the resulting, or the image of this femboy is this femboy here. Okay, so this is just notation basically, okay? So we are already packaging two notions into one string. So the notion of there being a map between these two spaces and that this is exactly the image of this femboy. So that we're packaging both those notions into this one string. So also given two subsets A and B, not the ball, okay, in given two subsets A in X, so you have an abelian group, abelian block in X, and so these are two subsets A and B in Y. This time B is in Y. B is in Y. This string here, or rather, phi that takes ordered pair X with A and takes it to Y with B. So now, more notation here. This is a more general form, given subsets now. This implies that, of course, X is mapped onto Y, but most importantly, the image of all the image of A, or the image of all elements of A in X is precisely all elements in B in Y. Yeah, or at least the image of all elements in A can be a subset of B, or is a subset of B. It doesn't necessarily have to all be elements in B. It can be the function, or the phi can really be phi can be a general function, or it can be surjective, or it can be injective. Okay. So this one here is a more general description of this notion here. So I'll write it down here. Phi of x0 is y0. So given this map, of course, given this map, we get a new map, which I will call phi A, that maps the fundamental group of X with base Femboy x0. So we're not restricting it to simply connected spaces now, but it could be any space with a given base Femboy, and takes it to phi 1 of y with y0 base. So the fundamental group here is taken to this fundamental group of this Femboy, well, such that given some homotopy class f, well, f gets taken, because when we take this map phi, the fundamental group is essentially a collection of loops, right? A collection of maps f. Or a collection of classes of maps f, homotopic classes. Yeah. So this here, we're essentially mapping curves onto other curves. So f here is taken to a new entity, which is phi composed with f, or the class of all compositions between f and phi. So perform the map f first, which essentially constructs one curve, and then perform phi on that curve, make it to another one. And f is essentially, taken to that one here. Okay. So if this f here is a homotopy between some f0 and f1, then phi composed with fi is a homotopy between phi composed with f0 and phi composed with f1. So these are curves, okay? These are not images, these are curves themselves inside a class of curves, which are elements of the fundamental group. So the generating set of these groups is essentially a function space. Okay? There is a set of functions in this space. Okay, so now this here is well defined. That's one thing. So 43 minutes. Okay. Given some f and g inside here, so we have two new maps, two new curves, or two new loops, I believe. Yeah, two new loops inside this fundamental group, f and g. Inside this this pi of x at base Femboy x0, such that, well, phi composed with f concatenated with g it's equal to phi of f concatenated with phi of phi composed with g Now, since both here are given by some s that gets mapped onto this piecewise function, phi of f of 2s for s inside the closed interval 1 to 1/2. And phi is mapped, phi of g of 2s minus 1 is s inside the closed interval 1/2 to 1. So we split it in half. So we're just saying that this is true because s can be taken to these two values over here. Now here's when we do sort of apply a little bit of category theory in the study. So let's say now, instead of just having two subspaces of f, let's have 3 of them. So they have their own corresponding fundamental groups, and then they have a certain map to them. So I'll write it down here. So if the first one, we're going to reuse x and y here with their base femboys x, x0 and y0. So x and its base femboy are taken to y with its base femboy, which is taken to a new one, z, with a base femboy z0. Z here is not the integers, okay? It's another space of femboys. So if this is taken to this via phi, and this is taken to this via psi, so these guys could be any class of homeomorphisms here. So we index the members of these classes, right, or any homeomorphisms by an asterisk. Now since phi, psi of phi of f is the same thing, okay? It's an element of the class of homotopic loops inside, inside the fundamental group, basically. So psi composed with phi of f. We have that. Again, sorry for the noise. I really couldn't find some peace and quiet today. But hope you guys bear with me here. Okay. We have that psi composed with phi star is equal to psi star composed with phi star as maps phi 1 of x naught taken to phi sub 1 of x z with z naught. So we are essentially taking this to this and then this to that. So we're essentially proving associativity or transitivity. I mean, we're showing transitivity between these two maps here, these operations. So the identity map of this space here, x, or this space of femboys x, which sends every femboy just to himself, right? That's an identity after all. So the identity induces some map from the fundamental group of this space to the same fundamental group. So if I take this fundamental group and apply that identity function, which is denoted ID, this is taken to itself only. So maybe just multiply every loop with 1, scale every loop with 1. If we represent every curve inside the fundamental group by a bunch of, or a string of vectors, or a string of vectors in a vector space, scaling those vectors according to this identity function just returns the same vector. So we're just multiplying every vector that we represent that curve to be by only 1. So nothing changes between them. So that's an identity. Now, astoundingly or amazingly, we can say that this here, that phi 1 is, bear with me, is a functor. So it's a functor. it takes in a bunch of curves that we can construct in X, some specific curves which we defined in the last lecture, and then puts them into one collection in a separate space. Not precisely in X, though there would be an intersection between that new space and X. They're taken to a new space. In fact, this here, pi, is a functor from the category of all base topological spaces. These are all base topological spaces. Every topological space identified with a base point. Like say R with equipped with 0. That's a base topological space. Now, it's a functor. It's a morphism, right? It's a morphism from the category of base topological spaces, all of these guys, to the category of groups with group homeomorphism. Because in fact, this is a group, right? So every possible fundamental group here that we can construct from any possible fundamentals, every possible base topological Femboy space is essentially a subset or just a part of the category of all groups with the group homomorphism. Because of course, every group needs to have an operation or a corresponding homeomorphism that we can do on its elements to make them into one another. The category is just a more general notion of a structure, mathematical structure. So a more general version of a group, more general version of a groupoid, of a magma, of a ring, stuff like that. So it's pretty neat that we have this correlation between category theory and algebraic topology. Now we haven't really gotten much to categories yet. Maybe I'll make a footnote discussing about that in Femboy theory. But what's neat is that we can think of this set, essentially. This is sort of a set, or at least the underlying set of this. This is actually something that's equipped with an operation, right? It takes something, and it gives out something. So it is a function. But not really a function in the normal sense, but a morphism between two categories. And that's amazing that we can make that distinction and that connection. And this is another reason why category theory is very important. We get to see this in a more higher lens. We get to see all this beautiful action between femboys and lines of femboys as a new object. As a new object. We used to think of this as just a set, right? As a structure in itself. But now we think of this as a machine between one set, one gigantic mother set or a universal set, and another gigantic universal set. And that's the beauty of it all. Really beautiful. So next, now a corollary from all this. I'm not going to prove it again. I'm not going to prove this thing. We're all about the intuition here. But we want to maintain some form of rigor. R2 or F2, since we're modeling F after R, we can say here that F2 is not homeomorphic, to R, F, N, for N not equal to 2. So you notice that this is a two-dimensional space. We cannot stretch it into a three-dimensional space without endowing the current pair of points x, y with a new number or a new coordinate z. We can't just squish this onto three-dimensional space. That's impossible because this doesn't have depth. I mean, unlike a container which we can split up open, or two sheets of paper, we can make them bulge out into the third dimension. This here is an infinitely flat material or an infinitely flat space. We cannot just bulge it outwards. And another reason why it's not homeomorphic to Fn is because these guys have fundamentally different fundamental groups. Now, when we try to, let's take an example, S1. S1 has a fundamental group of 0. But note that B2 or S2 is not precisely homeomorphic to S1 because we have to squash it down. We still have to squash it down. And because of that, we lose some points. Some points get mapped onto the same point. Okay? But the homeomorphism over here is mostly bijective and injective, which means that it's not likely that 2 points are gonna map onto the same point, right? We don't want it touching itself, and then we don't want to lose space. So this is the reason why S2 is not homeomorphic to S1, and thus, the entire space around it, its ambient space, is not homeomorphic to a space lower in dimension to it. We want it that when we morph these things under of course our homeomorphism, we want it such that everything is distinct. They have their own distinct images, and they are mapped onto separate points, not the same point. And because we squash all space onto, because we squash an extra dimension down to a lower dimension, we are having separate points in that higher dimensional space mapped onto the same space on the lower dimensional space. And we don't want that, because that makes things, that makes the homeomorphism, not a homeomorphism, but simply a function that is surjective only. Homeomorphisms are bijective by nature, by definition. So we can't have that. And it's the reason why F2 is not homeomorphic to any other space that isn't itself. Well, F2 is homeomorphic with itself. We can squish however we want, which way we want. We can stretch it and stuff like that, but we ultimately cannot bring this to another dimension or lower without breaking some rules about bijectiveness. Okay, so if we continue from our from retractions and contractions of spaces, given some space, or given the unit Femboy sphere, Fsn, n Femboy sphere, Fsn, without some Femboy x, this is contractable. So this is contractable. This is contractable, and any map, any curve, which we will call f that maps 0, 1 onto Fsn. Fsn is homotopic. Is homotopic to a non-surjective map, which is f minus 1 of x, which is a subset of 0, 1, which is compact. So yeah, we still have 2 minutes, but Fsn, if we take away a femboy from the unit Femboy sphere, or n Femboy sphere, this entire thing here is contractable, and any map, well, f or any curve inside this is homotopic to some other reverse curve. So if we embed a curve into here, or if we take a line of femboys and then put it inside or on this here, on the surface of this, we can essentially take that line of femboys out and then take them back, or take each femboy and put them back into their respective boxes. So that's what this is saying. And this contractable part is basically saying we can squish this all into one space, right? We can squish this all into one, or if we embed another sphere inside here, we can map every femboy onto a distinct, other femboy in that smaller sphere. And so I believe that's it for this lecture. Now, if you guys feel confused with the chronology of these videos, I suggest you guys check out the playlist tab of this channel, because these lectures are recorded separately, and not really separately, but randomly. So one lecture from a different course can follow a different lecture from another course. So if you guys feel confused about the entire shtick and why I seemingly talk about physics while talking about why I have a lecture of physics and then I make a lecture about math, it's because I record these lectures on the same channel, and that they are the same. They are uploaded back to back. So I suggest you guys check out the playlist tab so you guys would know the proper arrangement of these videos. And you'll notice also in the description of the video what exactly these lectures are. So if I'm not gonna stall any further, I don't want you guys to get more disturbed or more distracted, stuff like that. So I'll leave the rest to you, and this is a good place to stop.